Welcome back. We were talking about overparameterization and its benefits when it comes to non-convex training problems that we have to deal with when we optimize deep learning models. And we saw that thanks to overparameterization, we could be under the interpolation regime, and we leveraged that fact to establish faster convergence rate for stochastic gradient descent. Okay. Now we're going to talk about another benefit of overparameterization, which kind of enables us to actually provide a stronger guarantees. Okay, so not only we converge faster, but also we converge to better solutions. So what's the idea? The idea is that we are optimizing these models with these nice algorithms based on gradient descent, stochastic gradient descent, and their extensions. Okay, so we are not using in particular some classical optimization algorithms or arbitrary optimization algorithms. And these local algorithms are nice in the way that the landscape of the loss along the trajectory of these iterative methods looks very, very nice. And we're going to talk about what we mean by nice here. But what that enables us is to actually converge to optimal solutions. Okay, so it doesn't matter how the landscape looks in general. If we just zoom in on the landscape along the trajectory of our favorite algorithms, then the trajectory looks very nice, and that leads to these methods finding their way towards an optimal solution. Okay. So what's the idea? So the idea is that in addition to smoothness, the main assumption we've been imposing when analyzing these methods, we also have another condition, and that condition is called gradient domination, or Polyakov-Washevitz condition. So what does that mean? So the condition, as the name suggests, is saying something about gradient being dominant. So it is saying that the norm of the gradient square bounds up to some constant mu, the suboptimality gap. Okay? What's the implication? The implication is that, well, norm of the gradient was our notion, the natural notion of first order stationarity. So this condition is saying that first order stationarity implies global optimality. Okay? So in particular, all stationary solutions are also global solutions. Note that this was a property of convex function we talked about as part of our background lecture on optimization later on previously in the course. But this condition could actually happen despite non-convexity. There are non-convex functions that satisfy this condition. And in fact, all we care about is this condition being satisfied along the trajectory of our stochastic gradient-based methods. And indeed, it will be satisfied under certain assumptions. Okay. Now, why this condition is nice? Because you can use it along with the smoothness, notably the consequence of a smoothness that we talk about, to show faster convergence for gradient descent, in particular linear convergence of gradient descent to a global solution. And you can also basically show that a stochastic gradient descent under these assumptions can also converge sublinearly to a global solution. Again, despite non-convexity. Okay, so despite non-convexity, we can find a global solution. Now, what we're going to talk about next is that indeed, under some assumptions, this condition could be satisfied if the models are overparameterized. So it basically, again, demonstrates that overparameterization helps us not only intuitively in terms of increasing the capacity, the learning capacity of our models, but also in terms of improving the convergence properties of our training algorithms. Okay, so to demonstrate this, we're going to consider a simple task where we have n data points. And we just assume that we are in the supervised learning setting. So it means that I have features and labels. Okay. So in this case, I'm going to just, again, for simplicity, consider a regression task, which means that I have a bunch of features. They are p-dimensional, but the label is a scalar and it's a real number. Okay. All right. So for this problem, we're going to consider an arbitrary deep learning model, which is obviously parametric. So I'm going to denote that model by H. So it takes as input the feature X. It also depends on some parameter that we want to determine as part of the training process. And it's going to predict what the label associated with the input feature is. Okay? So using the fact that a square loss is a very natural loss for regression problems, thanks to its connection to maximum likelihood estimation we talked about, we consider the following simple empirical risk minimization task, training task, where we want to minimize the average loss, where this is how we define the average loss. Okay? So how much we deviate from the true labels, and the deviation is quantified through the lens of a square loss. Okay? Now, if we define a bunch of vectors and matrices, okay, we can actually write this training task in this nice compact form. Okay. So we just basically define these vectors y and h, which kind of gather the different labels and different output of the model as part of the vector. So in particular, the ith component of y is basically the ith label in our training data, or the ith input, the ith coordinate in this vector h is basically the prediction of the model on the ith feature. Okay? So both of these are basically n-dimensional, where n is the number of data points. And similarly, we also define this matrix X that gathers all of the training data points, the features, as its rows. Okay. So in particular, the first row is basically the first feature, the second row is the second feature, etc. So therefore, this matrix is going to be n times p, where again n is the number of data points and p is the size of each feature. Okay. So we define these quantities and we use the definition of the Euclidean norm, which basically is saying that the norm square of an arbitrary vector A is basically just sum of the absolute value of the coordinates square. Okay. So using this fact as well as this definition, we can write down our training task in this very nice compact form. Okay. Now, what is our goal? Our goal is to sort of demonstrate that the PL condition is satisfied along the trajectory under certain conditions. So if you recall, the PL condition was gradient domination. So we wanted to sort of relate the norm of the gradient square to the loss value. So therefore, it is natural to try to calculate the gradient of loss, and notably its norm square, to see whether there is any connection with the loss itself. All right. So we can calculate the gradient of loss quite simply. Sometimes matrix calculus is confusing, and I refer you to actually our notes on the basics of calculus to convince yourself that the gradient of the loss is going to be given by this quantity. Effectively, all we need to do is to apply chain rule properly to make sure that there is a match between the dimensions. Okay. Okay. So we apply chain rules properly, and this is basically what we get. Okay. So this is in the expanded form, essentially how the gradient looks like, and this is basically in the matrix form, if you will, where we again leverage our definition of these vectors and matrices that we defined in the previous slide. And here, in particular, this quantity is actually the gradient of this model h. Okay, so the boldface h, you can think of it as a vector valued function. Typically, for vector valued function, we talk about their Jacobian. Okay, but in this case, we work with optimization methods, so we kind of like gradient. So here we actually talk about the gradient of this vector valued function, not its Jacobian. And for Euclidean spaces, of course, gradient and Jacobian are the transpose of each other. Okay, so just a minor point. All right. So therefore, the gradient of loss depends on basically the gradient of the model and sort of the prediction error. Okay. Now, next step, we're going to talk about and calculate the norm square of this gradient. So in particular, we want to calculate this. So norm square is basically the inner product of the gradient vector with itself. So we know what the gradient is in equation 16. We just plug that in here, and then we get this nice quadratic form. Okay, so I have the vector of prediction errors transpose this symmetric matrix here times the vector of prediction errors again. Okay. Now let's look at this matrix in the middle. Okay. So let's call it a name. So let's call that K. So it is obviously a matrix that depends on W, our parameters. It also depends on X, the vector, the matrix of our features that we define. It is n by n, okay? And in fact, it is called tangent kernel. It is a positive semi-definite matrix as well, so which means that all the eigenvalues are non-negative. So as I just mentioned, we call this tangent kernel. And the reason we call it kernel is that the ij entry of this matrix depends on the interaction of the is and js feature. Okay, we call it tangent because it actually is constructed from the gradient, and in some sense, gradient is essentially like a tangent, or gradient determines the tangent line at any point. Okay, so that's why we call it a tangent kernel. All right. So now we're going to make an assumption on this tangent kernel. So we just mentioned that it is a positive semi-definite matrix, meaning that the eigenvalues are non-negative. But we're going to impose this condition that the eigenvalues, the minimum eigenvalue in particular, is strictly away from 0. So the minimum eigenvalue, I'm going to denote that by mu. And this is something that is strictly non-zero. So this is an assumption we make. However, I want to point out that a necessary condition for this to happen is that D, the size of our model, must be at least as large as the number of data points. Well, what does that mean? It means that overparameterization is a necessary condition for this condition. Okay? So as we're going to talk in a moment, this assumption in equation 18 is going to give us the PL condition along trajectory. Therefore, the implication is that overparameterization is a necessary condition for the PL condition to hold along the trajectory, and therefore leading to global convergence of methods based on stochastic gradient descent. So therefore, we can attribute the nice convergence properties of SGD-based method that we see in practice to overparameterization of deep learning models. Okay, so after imposing this assumption, the rest is actually quite easy. So we want to provide a lower bound on the norm of the gradient, and we can do that quite simply. So using some, again, basic properties of matrices from linear algebra, we can lower bound our quadratic form in the previous slide by mu times basically the vector of prediction errors transpose itself. So this is essentially the inner product of a vector with itself. We use that fact, and we write that equivalently in terms of the norm of the vector being squared. I'm also going to introduce this factor of 2 in the numerator and denominator. Well, this term here is actually quite familiar. This is precisely our loss function. So this is the loss that we were minimizing as part of the training process. Okay, so I use the definition here, and finally, I can for free subtract the minimum function value, because I know that we are minimizing the square loss, and the square loss is a non-negative quantity. So the minimum, whatever it is non-negative. So if I subtract that, I can get another lower bound. Okay, so I'm moving in the correct direction, if you will. All right, so therefore, we just established the fact that the PL condition holds as long as the minimum eigenvalue of the tangent kernel is strictly positive. Okay, and as we talked about, a necessary condition for that is overparameterization. Okay, so what's the implication here? The implication here is that if the tangent kernel is well conditioned along the trajectory, the PL condition holds, and therefore methods based on gradient descent and stochastic gradient descent converge very fast to a global solution. Okay. Now, how can we ensure that this condition holds? Okay. In fact, with some effort, we can show that random initialization can ensure this condition. So with high probability at initialization, if the initialization is random, we can show that the minimum eigenvalue is strictly positive. Okay, so that's nice. We can show that sort of the PL condition holds at initialization. Well, how about the rest of the trajectory? Well, if we can somehow control that we are not deviating too much from the state of the algorithm at initialization, then we can kind of expect that the minimum eigenvalue is also strictly positive along the trajectory, as long as we stay near the initialization, as long as the optimization happens near the initialization. How can we ensure that? Well, if we assume that the step size is small, or if we assume that the Lipschitz constants, the smoothness constants are not too large. So if you have those conditions, then the variation of the parameter is controlled. We stay near the initialization. We know that we have noise conditions near initializations. Those conditions will also hold with high probability for every point along the trajectory. So therefore, thanks to overparameterization plus noise initialization, we can kind of attribute the noise convergence of methods based on a stochastic gradient descent to overparameterization. Meaning that along the trajectory, we're going to have a very nice looking landscape which enables fast convergence and also convergence to global solutions. We talked about basically the benefits of overparameterization from the perspective of variance reduction, faster convergence, and also convergence to better solutions. Now, these were all things that are related to the training process itself. Okay, so how successful are we going to be in terms of reducing the training loss? It doesn't necessarily tell us anything about the performance of the model at test time. So that's a question about generalization. But we're going to address that in the next part of this lecture, and we're going to see that, again, under certain conditions, we can sort of look at overparameterization as a way that provides us implicit regularization, and therefore it could aid with achieving better generalization performance as well. I'll see you next time.